yours.
All right. Thank you, Helen. Let's
Hello,
just jump
Helen.
right in. Let's just jump right into it.
Yes, you can start.
Okay, strategies for non-qubit quantum computing. If that sounds like a somewhat controversial title, it's intended to be, because the whole idea of this presentation is to say that there are ways at going at quantum computing and the incredible power of quantum computing that don't necessarily have to start with the concept of qubit. So that's what this presentation is about. It's saying that, yeah, you can do a lot with qubits. Qubits are a well-matured concept by now, but the quantum world is more than just a set of binary decisions. So let's get into some of the history of that, where the qubit came from. Overview, I'm going to have actually four parts, main parts. Review the deep history of qubits. Where did this concept come from? Question some forgotten assumptions. And that's a good way to describe it. One thing that happens in research, and you can even see it in some of the papers I quote, you get someone makes an approximate model at some point and says, well, you know, you make these assumptions, all of which are wild assumptions. And you say, based on those assumptions, what do you come up with? And that's fine. But what happens next is the people that are quoting that paper then quote it as if it's an absolute solid fact, not a bunch of approximations, not an approximate model, not a guess, but it gets quoted more and more authoritatively as you go over time. So it helps sometimes to go back and look at the original assumptions, the original history, just to get an idea of where some of this really came from. So, and then I'll propose a few approaches. If you have watched my previous videos, you know that I do have a radically pragmatic recommendations for some aspects of physics. If you talk about Planck foams, I will point out repeatedly and say that is a mathematical extrapolation that has no experimental verification. And you can point to some things and say, well, how about the Casimir effect? Oh, that gets very interesting when you get into those issues. So I will, a radically pragmatic approach to physics where I say all the strange stuff is extremely real, but also some of the obvious things, like the idea that a vacuum is a vacuum, is actually an extremely mathematically helpful concept. So I'll touch on that a little bit. That's not the main purpose of this, but I can't get away from that. I will always bring in a bit of flavor that is not your standard. Humble origins. Now, this is something, if you've tracked qubits, I imagine you're probably not aware of this. A lot of the qubit discussion originated in the question of how do you model a methane molecule, which I think is hilarious. It's not what you would expect as the source of a lot of this discussion. Back in 1970, a fellow named I do not remember the first name, Schlieter, that might be almost correct for the German. I do know a little German. Was looking at an issue of how methane molecules are structured, what vibrations, you can see the highlight there. And this was a point where people have had the Schrodinger equation for a long time, for decades. And they say, well, how do we actually model this thing in detail? Computer technology was getting stronger all the time. So the point was that you just write down the quantum mechanical Schrodinger equation, 3 dimensions as it turns out, just for the single molecule, and try to figure out what are all the properties. And the thing that happens very quickly when you do that is it becomes enormous, absolutely gigantic, because you're looking at the Schrodinger equation as a smooth differential equation with infinite precision. And by the way, that's a point you'll hear me talk about at every point. Be careful as soon as you say infinitely smooth precision for anything, because that is a mathematical concept. It is not something that you can find experimentally, not surprisingly, because everything has a finite amount of matter and various other constraints. So it's a mathematical assumption, and it shows up vividly in applying the Schrodinger equation to a single methane molecule because when you try to model it, even a rough, just, as the guy says, too few, 10 points per each edge on this 42-dimensional lattice work, which is what you get when you start getting all the interactions between all the different quantum equations for all the Schrodinger equations for all the different particles, you wind up with this lattice work, just an unbelievable number of points, and obviously not calculable. So you go like, well, what do I do next? So this was, I think, genuinely a little unexpected when people got into it, because the assumption that the universe is extremely smooth at the level of atoms, that there's this continuous space, is so intuitive and so obvious if you're familiar with the beauty of mathematical differential equations, that it's just natural to think, well, it should work out well. But every time you try to apply it practically, it doesn't really help. So immediately what you go from there is you wind up, just as Feynman does and beautifully in his lectures, you wind up making a lot of simplifying assumptions. So when he talks about this, this even might be an indirect reference to some of Feynman's work, because Feynman talks about how if you do a lot of assumptions, you can actually reduce that to a much, much more tractable and even kind of intuitive structure. But still, you got this stark contrast between these different things. This paper is in German and in Russian. It's hard to find. I'll probably post it at some time because it's an interesting paper. And it kicked off some interesting further discussion. The high cost of digital modeling, which I've just mentioned on that, was then taken up by a fellow whose name is Russian. I will not try to pronounce it. That second little I there is sometimes translated as a Y. Poplaski, I don't know. Someone could, I shouldn't even try. He did an interesting model where he said, well, let's take that seriously and see what happens. This is a good paper, by the way. It's another paper that, again, is hard to access, hard to find, but it's a good paper. And I love the part where he talks about how the probabilities of fluctuations turn into two-state binary digits. He does a really good analysis of this. So it's a good paper, and it's unfortunate that it's not a little more accessible. I haven't fully translated that one, so I might try to put that up also. So I like his way of analyzing it, though. He talks about these things and winds up with a conclusion that you have a very strong limit on what a modern digital computer can do for these. So he's the one who first stated more clearly than the previous thing by Schluter. And then he gives Schluter's example and talks about, well, what would happen if you tried the most efficient calculation mechanisms we have using low temperature, every trick you can pull on the computational side. What do you get? And the result is, think about how ludicrous this is. We're talking about one methane molecule, one bloomin' simple, tiny little methane molecule. And yet that one molecule, to model it digitally, just even briefly, would require all the energy produced on Earth over a century at that time. Well, you don't have to think too far to see something is wrong with this concept, because if it takes that much energy in order to model a single molecule, what is reality doing? Because we're full of methane molecules. Are they all taking that much energy? No, of course they're not taking that much energy. So obviously the physical mechanisms, which have their own way of calculating, that's a thing that we forget. Physical world has its own way of calculating results. That's a good theme to keep in mind, because when the physical world calculates the structure, the vibrations, and all the methods of these molecules, it doesn't have these problems. And that should tell us that we're missing something when we try to force the natural world into our artificial, infinitely smooth, infinitely differentiable, extremely infinity-friendly mathematical types of models. There's a good chance that we're missing something in our understanding of what's going on underneath. Otherwise, reality couldn't do this. And maybe we're getting a little bit backwards. We're a little desperate because especially at this time, we had no way to model these things. So you can understand why they're trying to do it, but the calculations and the implications are pretty severe. Now, I'm going to put a kind of an intrusion on this. Going a little away from that theme, there was a fellow in 1974 who went off in a somewhat different direction. A guy named J.J. Hopfield. If you've kept up with the news, you probably know who this guy is. He got the Nobel Prize last year in physics, but he didn't get it for this. This paper was mentioned, and I find this uh, amusing, interesting, and strange. If I had to point at a paper that J.J. Hopfield should have gotten a Nobel Prize for, this is the paper I would point at, and another one that's similar from the same year. Um, and the paper that he got the Nobel Prize for, this one is mentioned in the award, but the one that he actually got the prize for, oh, I don't want to get into that. That is, I did a presentation on that quite a few months ago, and it's just an amazing mix of issues that go onto the other paper. This one though, is he was getting at something with his work with biological systems that we don't understand how these things do this. And the key finding he had was that when you're doing things like DNA replication, it doesn't work like a computer. It just doesn't. It has features that are trying to, what we would think of, compete negatively to the final conclusion. As he says, useless or deleterious complications, which are caused by some of these compounds. And any engineer would say, like, well, it's like putting a pair of scissors into your machinery. You don't want to do that. And yet, biology does exactly that. And then it switches it around almost magically and turns that into a positive interaction. Now, the reason I mention this in this context is the way they do that seems to involve quantum interactions that we do not understand. It's not a purely mechanical issue. You can't just take these things. If you tried this with real physical objects and you threw in a pair of scissors into your motor, well, the old throw a monkey wrench in is exactly what happens there. It doesn't work. It damages it. And yet at the quantum level, there are ways of competing, ways of interacting, that things that should be bad wind up being good. And I would make the assertion that this same thing where a methane molecule does all sorts of calculations we can't do is coming into play in this. And we don't really understand it. When you're at the chemistry level, you're almost at the mechanical level, but not quite. And the details of some of these interactions remain very difficult to model. So this was a good analysis because he's saying that there's something else going on in all of this time calculation. So a little bit of a tangent from the quantum computing, but relevant in terms of saying there are some other interpretations. First quantum computing hypothesis, I would argue, I think many people would argue, was not by Feynman. Feynman usually gets the credit for that, but I would definitely point to Yuri Manin, and I hope I'm pronouncing it right. Russian name, I'm not quite sure of the pronunciation, but Yuri Manin had a very interesting book, which is, the title is Computable Uncomputable. And uh, uh, it was a marvelous book, not actually a series of lectures that he gave, talks that he gave on Russian radio. And one of the things he comes up with was this idea that the behavior of these molecules, molecular biology, is just so incredibly smart, capable of doing things that we don't understand, that we needed a new mathematical model of how these things work. Now, the model, Manin's paper, that I've commented on this, he starts off with what I feel is an extremely powerful argument for saying molecules do computing that we can't do. But then computers were very much an issue in the 1980s and how computers apply to physics. So he kind of like just in the next paragraph switches to what's really a very different idea, which is a state of quantum automation via virtual classic automata. And as soon as you do that, you get this nice structure, and he points it out, unitary rotations in a finite dimensional Hilbert space. So it feels like a simplification in some ways, but there's some issues with this. And if you, like I say, this is, uh, I don't, I believe there's a full English translation of the book, but a marvelous little book. Bell actually riffs off of this title because he has observable and unobservable, I believe, is the title of his book. So that's an indirect reference to his book. Now, the thing about Mannen's hypothesis, okay, you jump from the molecular computation to saying, well, how does this go? How does this work in a broader spectrum? Uh, his observation is very much like that of Feynman's superposition of states, his analysis of all the possible realities, all the possible integral of future states, integral of all possible futures is how Feynman describes it. So Manin is referencing that kind of a concept. And he says that you have this quantum space with all these different projections or different versions of reality. Now, what he does there is a leap, and I'm trying to kind of emphasize that this is a leap. This is a big leap in faith when you do this. And the leap that he did was to go from saying that these individual small contributions to the overall path integral that Feynman talks about are actually each real. And if that sounds familiar, it's because that is the many worlds hypothesis, Everett's many world concept. You see it mostly in quantum computation via Deutsch, but it's still the same concept. Deutsch, in many ways, was more many worlds than Everett is. It's an idea that these worlds are entirely real as our world, and then that they all get together and kind of come together to a conclusion with that. Now, that's important, and that has had a powerful, powerful impact on decades of quantum computing research. I remember the early days. In fact, I remember I remember days so early I have trouble finding the references now. I distinctly recall statements in the early stages of quantum computation based on the Deutsch model that if you just had 15 qubits, that's all, just 15, not 15 million, not 15 billion, 15 qubits, that the system would be able to break every encryption that there is. And you look at that now and you laugh, say, well, of course you can't do that. You have all the error correction issue, which is what a topic that came up next. Nobody talked about error correction in those earliest days. They talked about just the incredible power of just a few qubits. And then the error correction came after those failed. So I remember that I remember that little hop sequence very well because it was kind of like, oh, okay, that didn't work. The reason they could make statements like that, and I remember trying to explain it to somebody myself, I say, they're accessing this idea of an infinite number of worlds, so the computational capacity is without limit. And I was a believer myself at the time of this. I thought, oh wow, this is incredible. If you can just get the quantum system going, you'll be able to do this fantastic access to all this different computational power. So when you see Manin talking about these virtual automata, now notice he's not talking about qubits. He's actually talking about virtual instances of processors in different universes all going together. Would not be too much of a stretch to interpret what he said. So it depends fundamentally powerfully on the idea of a many world interpretation, heavily under the Deutsch line. So that's something to keep in mind. Now, a little bit later, Richard Feynman, I'm a huge Feynman fan, by the way, came up with his interpretation in which he said, well, we have a universal computer for just regular functions that can do any function you want, a classic Turing machine type model, except, and he goes through just a beautiful explanation on why it does not work for quantum systems. And it's the entanglement issue. You point out that what happens is if you try to model the entanglement, which is instantaneous, watch out for that word. If you model the entanglement issue, which does not follow the regular rules of information travel, you find out that your computer just comes to a screeching halt for even trivial questions. There's just too much delay in trying to get the systems to correlate properly if you don't have a quantum type of concept. And Feynman does a really nice job in this paper of going through that issue. I recommend this paper highly. It's a very cool paper. And then he proposes, can you do it with a new kind of computer, a computer that incorporates quantum mechanics? Now, here's one of the differences that he used quantum mechanics more as an emulation concept. He's saying that we can't do this, but what if we borrow an existing quantum function and then put that into use for doing these other computation? And first, I think first couple times I read his paper, I did not notice this little qualifier. That he then goes on and says, well, can we create little lattice works of like spins and other things? Feynman has a very informal way of referring to things, and which I like because sometimes he uses that to emphasize we don't really know. So he's saying spins and other things. Yeah, have to figure that out. This comes really close now to the more modern concept of a quantum computer. In fact, if you take the idea of spins and translate those into qubits, which you could certainly do for electrons, then you wind up getting very close to the concept of quantum computer we have now. So brilliant paper by Feynman. He goes in much more detail than Manin did on the introductory work and expands on it. But Manin should get credit for some of the earliest work on this. Qubit. I I love the origin of the word qubit. Any of you who are out there who are churchgoers, biblical scholars, you've heard the word qubit. It's the length of measure of Noah's Ark. So it's so many qubits this and so many qubits that. And Ben Schumacher and Bill Wooters, I assume it's pronounced Wooters, I'm not entirely sure, were having a car drive and they were just chatting along and Ben Schumacher was quite frustrated because he kept trying to measure quantum systems in terms of conventional information. And then he suddenly realized that, well, maybe that's just the wrong idea. Maybe it's not information at all. Maybe it's not bits at all. It's some new kind of quantum information that we could call a qubit. And then they just both died laughing because they thought that was hilarious. They were referring to the qubits from Noah's Ark. So if you hear that and say, oh, that sounds like the biblical reference, that's not an accident. That was that, and that was part of the joke. Interestingly, Schumacher doesn't remember for sure if he's the one who came up with it, but Wooters is unequivocal. He says, yeah, no, Ben was the one who did that. He came up with it, and we both laughed, so he remembered it quite well. So the idea is the qubit, instead of being kind of like a one value system, it would be a two-level system. It gets a little flaky on how you interpret the terminology because, of course, a bit is a two-level system. It's 1 and a 0. It's got two value system. The qubit, though, would have two forms of measurement going on. So it has two units. How exactly he would interpret two levels in that, it's a little fuzzy on that. But the idea is that it's something more than just a binary switch back and forth. In fact, if you want to go to a good explanation of what that looks like, here's an actual calculation diagram complete with amplitudes. So there's nothing radical about these figures, although I've done my own version of them to try to explain the idea. The idea of the two levels is maybe better thought of in terms of saying you have two orthogonal dimensions, just like your wall is orthogonal to your floor, that x is orthogonal to y. If you have a value along the x-axis, it only shows up as a point in the y-axis. It has no dimensionality to that thing. So this is kind of where Schumacher was getting at, the idea that you have a bit, but the bit is being viewed from two different perspectives. And if you think of shadows, that's not too bad of an analogy. So you can imagine if you want to turn these diagrams a little bit sideways so that they're actually like a wall and a floor, you have this rod, this green arrow that's extending upwards. It has a unitary length. It's like a bit. In fact, it is a bit. But the bit has this weird property that you can angle it at different degrees between the floor and the wall. And then you take the shadow, which is called the dot product, of each of those directions. So you see the shadow of a light going horizontal and the shadow of a light that's going vertically or going down. And they each cast these different shadows. which are called the amplitudes. You want to use complex math for this because complex math is just beautiful for this stuff. It just has all sorts of marvelous properties for that. But the concepts, you can just look at it in terms of a figure. Then you take that item called an amplitude and you square it. You actually double it, you make a square out of it, and lo and behold, you come up with your prediction. And the two squares are guaranteed to add up to a single unit. And from that single unit, though, you get the probability that you'll wind up either with the up or down or the two different states. So this was really the clever innovation that they came up with, was quantify this. And if you notice, it's following along the lines of what Feynman was saying. Feynman was saying like, oh, can we somehow take this and make everything into a small quantum effect, and then we combine them all together and we get a big quantum effect. So we have a universal quantum computer. So this is very much tracking with what Feynman had been suggesting, and not coincidentally either. So he says that, yeah, you still have one bit, but you have these different ways of interpreting it. Now, here's a subtle point that I want to point out here, and this goes back to the Everett-Deutsch mini-world model. There's two ways of looking at this figure. One is that the projections that you see, the shadows falling, the blue shadow and the red shadow, that those lines that they form, the amplitudes, are actually real objects, that they are objects in their own right, and that they have their own existence, and then they contribute to form the green arrow. So it becomes like a vector sum. If it's exactly what it is, it's a vector sum of those two amplitudes. So you add the two amplitudes, and this is the basis of quantum math. This is how everything works. You have these linear sums. It works out beautifully, gives you all sorts of interesting properties and ways of handling these systems. And it's really not that complicated. You just keep adding things together, and you wind up in saying, oh, I don't have any weird interactions between the parts. They just sum together, and I wind up getting this reality. The subtle part is which comes first. Because if you say that all of the shadows are real, all of the different superpositions, all of the different possible states are completely real, then what you're really saying is the many worlds interpretation is correct, which is fine if you want to go on the many worlds route, because you're saying that, yeah, each of those represents a real angle, a real thing, and then we see a shadow of it literally in our world, and they combine together to give this green reality. So you can do that, but you can also go the other direction, which is in many ways simpler. Is you say, if I have a shadow, it's an object that's leaning, the shadow is the secondary part. The object is the real part, and only the object. Now, if you take that interpretation, then this green arrow becomes the only reality, and these other parts, these view angles, become part of the context of how you view that entity. So in some cases, an electron looks like a 1. In some cases, that would be the left case. In some cases, it looks like a 0. That would be the right-hand case. And in other cases, it's kind of in between, because there's a real concept there, but until you do this little observation thing, you don't actually have it forced into one of those states. So interesting interplay of concepts, but a surprisingly critical concept of which is more real, the projections or the original object. Now, I'm going to switch tracks a little bit, part 2, and talk about something called Fourier transforms, which I'm sure some of you, many of you are familiar with, but it's relevant on how to take this idea of qubits to a somewhat different level. And it's not irrelevant either. Back in 1994, a guy named Don Coppersmith, I don't think he's well known, I think he should be better known for this really, he noted that the Shor algorithm, the interesting part of the Shor algorithm is just analog computing. And I know that from direct conversations that some exchanges I had with Shor at the time, because I was talking about, can't you do part of this by analog emulation? And his response was, well, yeah, but you got to get back to this entanglement part. And he's exactly correct. So I was just focusing on saying, like, what can we do with the analog part, the conventional part? And part of getting that non-classical part, that entanglement part, the same thing that bothered Feynman so much, the same thing that leads to this explosion in the number of points. How do you model that point? And part of it was to use a Fourier transform. So Shor had an approximate way of doing the Fourier transform. Coppersmith came up with a quantum version of the Fourier transform. And he applied that and said that this is a way of getting he showed that he could do a much better version of the algorithm using quantum mechanics itself as part of the Fourier transform. I'll get into what a Fourier transform is in a minute here. But he showed remarkable drops in the complexity. So this idea of a Fourier transform clearly has relevance to a specific case of the Shor algorithm for quantum computing. So I'll use that as a leaping point. For me, this was actually, I came about this the other way around. I first was speculating about the power of Fourier transforms for a long time because I think they're just amazing at the quantum level. And for a long time, I was not familiar with the quantum Fourier transform that Coppersmith had come up with. So for me, this connection point is a little bit backwards. I was saying like my speculation was that the Fourier transform is extremely relevant to quantum computing. And lo and behold, I'm looking around and going, oh, that was what they eventually wound up doing, what Shor wound up doing to handle this. He used the Fourier transform to express the quantum part of this problem. Fourier transform, here's the mathematical equations, for those of you who like, and I see that I didn't quite get, I changed the xi to a k everywhere except there. That should be a k there. So I was using a wave number instead of that equivalent concept. But yeah, pardon this little glitch right there. That should be a k. I'll get that fixed in the online versions. And then you have the inverse Fourier transform, which goes in the opposite direction. Beautiful symmetry in these things. Fourier transform. I would argue this is literally one of the deepest symmetries of the entire universe. And there's reasons for saying that. I'm not just saying it as a casual statement. I'm saying Fourier transform really, really goes deep into the nature of reality, especially quantum reality. So what is a Fourier transform? You've got, first I mentioned this, you have one reflection of that fundamental nature of the Fourier transform is that there are two forms of your wave functions. And I don't know how much this gets emphasized these days because it seems like in many ways we've gone to a very position-ish type of viewpoint. But this is a very well-known feature of quantum mechanics, especially a lot more discussion about it in some of the earlier papers. You have two versions, position wave function, which for a single particle looks like a wave. The trouble is you have those entanglements and then it becomes a wave in a high dimensional space and you get to 42 dimensions and all that. But for the simple case of like, say, one particle, one electron in a box, it really does look like a wave. It just looks, just like a wave, a standing wave, and has all these functions. So the position wave function version of Schrodinger's equation gives you what you would expect. But what is really interesting is that you can flip it upside down and go to momentum directions. You can have momentum in X, Y, and Z and create a new space in which you can put the same particle in the same space and wind up making the same predictions. The two have a mathematical equivalence to each other that's not obvious, it's not trivial, and produces different ways of looking at the same problem. Now, there's no reason to think reality should work this way, except that that's the way it does. And the fact that it does gives an extra set of tools for looking at a whole range of phenomena, especially if you look at the momentum wave function, some of the stranger and squirrelier things that quantum particles do, you get that through the momentum wave function interpretation. I'll mention something in passing. This is a misconception. When you have a particle in the position wave function, the particle is modeled as a single point. So you have a little tiny point, and that point goes around, and you have the wave function around it that gives the probability of finding that. When you go into momentum wave function, you still have particles. They still interact with each other, but they do not interact as points. And In fact, I cannot think of a textbook that says this explicitly. Used to have textbooks about these shells, but they don't say this is what a particle looks like in momentum wave space. But they do. A particle that is a point in position wave function actually turns into a shell-like shape, and then the shells are nested when you get in momentum space. So if you see a Bose condensate representation that shows them as little points, that's not correct. It's not that simple. The transform goes much deeper than just you change the entire shape of the particle to do this. So we have this marvelous symmetry though between these two. Now, what is a Fourier transform? I'm going to give this is one of multiple models I've done to try to quickly explain the Fourier transform, but I like this one just because it has a certain simplicity. Imagine a bunch of sine waves. Just give the sine waves as a given. Okay, fine. So you got some sine waves. Then you have a peak, and you say, how many different sine waves can I fit to that peak? Well, you don't have to look at too much. You say, well, essentially an infinite number of sine waves fit on the peak. In fact, it doesn't stop until you get to this little blue section here, and then you get a cutoff. The sine waves, you can't get any smaller. If you get any smaller, you wind up with a different peak. So you wind up having this concept. You get a whole bunch of wave functions up to a certain point, the highest energy point, that gives you the limit of how sharp that peak is. And then you have all this, literally an infinity of other waves that go out beyond that. That's your Fourier transform. It's saying that if you take all the sums of all these different waves, which all add together constructively at this one point, and by the way, I'm not entirely sure. I assume my mouse is showing up. I hope it is. But I have this one point here where they all add together constructively. But if you look over here, what happens over here is chaos. And they sort of add together here, so you get the drop off, but then everything becomes chaotic noise. Now, if you can get that, you've got the essence of Feynman's path integrals, how they work. You get the essence of how every Fourier transform works. So you get the essence of these, why you have these two relationships. And also, you have the explanation for why you have a Planck's constant. Planck's constant is the negotiator between these two spaces. If you have a broad location momentum and frequency space, if you have a sharp peak, that means you have this broad momentum space. Well, that momentum space is its own space. So you have this enormous number of points in that space. And what you've said is, if I make this thing sharp in XYZ space, if I make a point so it's very small, then the Fourier transform of that is going to be enormous. It's going to be gigantic. It's going to have everything imaginable up to a certain cutoff point, which is the energy limit of how much is involved with this. This actually is the basis of quantum uncertainty, of Planck's principle. Planck gave the constant, not knowing that this what it was, but he gave the constant that allows you to go back and forth between these two representations of the same thing. Once you get into the other space, another thing happens. You can interpret this as a position in momentum space, in which case the XYZ locations turn into sine waves, which is a kind of a strange thought, but actually works very well. And then you map out all these frequencies, and they're spread all over everything. So when people talk about a perfect momentum state as having no location, that's what they mean. They're saying that it has the sine waves that represent space locations just don't, they cannot have a single location. If your Feynman lectures have some beautiful discussion of that, Feynman's book QED has an even better quick discussion of some of these issues, but these are just marvelous little symmetries that you get. Now, here's where I get into some different ideas that start getting closer to the computation issue. Lenses are Fourier transformers. And you may not think of a lens that way, but on the other hand, think what a lens does. You put a big diffuse area of light and a whole bunch of light coming in here. And somehow that silly object transforms all that light to a bunch of singular points. Here, there, here, here, here. And I can remember when I was a little kid, I could not understand how lenses worked. I was so amazed when I found out that a lens is ordinary glass. I thought it had to be some magical substance that magnified the image. And then I finally found out somewhere this is back in elementary school, that, oh no, it's just the curvature of the lens. I just thought that was the most amazing thing. I said, how can that be? It just didn't feel right, because I'm saying, why should the curvature make a magnification? And this is getting into part of the reason why, because that curvature transforms a huge area of waves into a single point. And that's a kind of a magical property that lenses have. So we see this, and it is a Fourier transform. You're taking planes of waves out this side, and then you transform it into the points, well-defined points there. But what's really neat, is that this is quantum mechanical. Did you think of yourself as using quantum mechanics while you're reading and looking at these slides? You should, because if it wasn't for quantum mechanics, you wouldn't be seeing anything. Everything light would just stop the minute it hit anything, because it would just scatter and go everywhere. But that's not what happens. A lens has this remarkable property. It takes a huge wave representation of a single photon, not a bunch of photons, one photon, one silly photon, behaves as if it's a gigantic wave that comes to the lens focuses it down, and then you wind up with a single point. And if you heard that quantum mechanics is always about uncertainty, that's not true. There are cases where quantum mechanics is about certainty, and this is one of them. If you radiate a photon from this area here, you can spread that photon over a huge amount of space, and yet when it gets here, it winds up with 100, well, close to 100% certainty it's going to wind up right there. And if this was not true, you wouldn't be able to read. You wouldn't be able to see. You couldn't see these slides. This is how all of vision works, is a Fourier transform mediated by a lens. So the fact that it works at the photon level is what's so remarkable. And it shows you that people get in debates. They talk about, is a wave function real or not? The behavior of the wave function can be an extremely good tool for understanding how to predict where the particle winds up. Now, if you want to get into philosophical debates about what that means, it looks like a wave, it smells like a wave, it travels like a wave, it obeys the speed of light like a wave. It has all the structure of a wave. It's just that if you look at it too soon, the wave disappears. So yeah, you have a little bit of a conundrum there. But it certainly behaves just like a powerful wave. You take a powerful wave, you see it very explicitly. Yeah, it's a wave. The trick is that if you keep making that wave, that powerful light source more and more dim, the behavior doesn't change. So you get down to having one photon, and the behavior doesn't change. It behaves and focuses through this lens exactly as if you were trying to do it with a powerful wave. That's a remarkable thing, and it's one of the deeper mysteries of quantum reality. So, and here's a point that, in some ways, I would put this as the focal point of this slide. If you want to have an understanding of how nature does things with incredible efficiency, you should look for cases in which nature does something with incredible efficiency. And one of the most explicit examples I have ever seen anywhere in physics is the focusing of a single photon through a lens, because it doesn't care. Photon Fourier don't care. You can take that one photon, same photon, go through a tiny little lens. It could be less than 1 millimeter, but just picking on 1 millimeter. And it focuses to a nice point with 100% reliability of getting a little dot, a little photon reception. But you can also do the same thing with a lens that's about 4 million light years across, and you get the same result with the same photon, with the same, I won't say the same reliability, because your lens obviously is pretty weird shaped lens, but it doesn't matter. The concept is the same. And you worry about, so, well, this is gravity. It doesn't matter if it's gravity, a lens, or whatever. A lens is a lens, it's a lens. When it comes to photons, the photon does not care what the lens is made of. It doesn't care what force is involved. It doesn't care whether it's gravity or strong force. It doesn't care. It just says, oh, there's a lens. The lens is telling me to go this way. And it winds up, so you have this little tiny point, and you get the same result. Now, how many other phenomena do you know that can take a measure of energy that's so small that we can barely measure it, send it out over a lens 4 million light years across, and wind up with the same result as you get with a microscope with a 1 millimeter lens. That's efficiency. That says you did a Fourier transform that you said over 25, again, 25 orders of magnitude is an underestimate. There's no reason to think why this isn't like, I don't know, add as many orders of magnitude as you want. That one photon can go through an entire set of, it's about 4 trillion suns worth of galactic matter. And if it doesn't hit anything on the way, which it can, but if it doesn't hit anything on the way, the gravity focuses and you get this lensing effect. Now, how can that happen? People want to, it's our intuition that we want to think of the photon as a little tiny point. And of course, Einstein recommended this, so it's not surprising that we do it this way. We think of the photon as a little point particle. But when you get examples like this, you're like, well, that may be, but how? What? How did this happen? And the correct is we don't understand how it is able to do this kind of scaling. This incredible efficiency, incredible scaling of a single photon to essentially probe the shape of an entire gigantic galactic cluster and then come out with a result. It says, oh, okay, I add all that together and I get this. So the bottom line is, even though we don't understand how this works, it does say that the Fourier transform in nature, under the right circumstances, is very close to free. Now, the other catch is that when you see that one photon, how much information does it give you about that galactic cluster? The answer is nothing but direction. You have one photon, you say, and this is what astronomers do all the time. They say, like, something's out there. I see a couple photons. Little red dots are the popular ones these days. So they see a little bit of a few photons. They say, something's out there. We just don't know what yet. So you start accumulating more photons. This is what astronomy is all about. So I need more photons. So here's the relationship. The transform itself is scale free, is almost free. You can do it with a single photon and get information, but the cost is in the details. So you see this where you have to get a lot more photons before you start seeing the details of the galaxies on the other side of that lens. So more details, more energy, you get more details. But the Fourier transform itself cost almost nothing. Now, if you notice, there's a certain similarity to quantum computing. What are we doing these days? Everybody's saying like, well, if we get 1,000,000 qubits, then we'll have enough resolution, really, to get that final answer. That's not a coincidence. There's a deep underlying quantum relationship between those problems. You get enough qubits, you get enough detail, if you can keep them entangled, where you can get that result that you're looking for. But the actual cost of the transform itself is not the issue. It's the details that matter in the end. So how relevant is this? I would say extremely relevant, because Fourier transforms via photons, not just the artificial ones we do with computing machinery. Scalability over at least 25 orders of magnitude, check, that's good. Vanishingly small energy to get you 1 bit of information, check. That's a pretty important piece of information from that 1 bit. If you think about it, you know the location of an entire galactic cluster from that 1 bit, at least the direction of it. Extreme speed, because literally it's at the speed of light. You can't get faster than that. The lensing will slow it down a little bit always, but there you go. Now, the quantum Fourier algorithm is not done using photons. And this is something I want to point out. If you want a specific example out of this lecture, or say like maybe something could be done there that would really help your quantum computing, this is it. Is if you find a way to uh,
Yes, you were on the slide. Yeah, this is it.
This one, or I just switched? This one?
Yes.
Okay. All right. I don't think I lost too much there.
Just a couple
That
minutes.
I'm going to go to a wired connection. This is a good explanation of a good reason why. So let's continue from here. How relevant is the Fourier to quantum computing? Well, you have scalability over 25 orders of magnitude, vanishingly small energy, extreme speed, literally the speed of light. By themselves, that's not proof that it's going to help you in the quantum computing, but you do have the 1994 Coppersmith quantum Fourier algorithm, which shows that it is relevant, that you can use the Fourier transformer to achieve some of the non-locality issues. And that's not surprising because think about what Fourier is all about. It's about taking an enormous range of waves and compressing them to a single point. So that's really the essence of non-locality. Or that the idea of entangled over a huge area fits well with this idea. So it's not really that surprising that Coppersmith said that if you use a quantum version of the Fourier algorithm, you get a better result. Now, my point, though, would be as an opportunity. The Coppersmith algorithm is not an optical, as this, unless there's implementations I've not seen or found a paper for. The Coppersmith is not a photon-based optical Fourier quantum Fourier transform. There are photon-based quantum Fourier transforms that should be much more efficient than anything we can do with a purely qubit approach. So I think there's an opportunity there that if you're interested in getting a good implementation, you should look for these very low cost, very powerful optical approaches that are not strictly qubit, but they do have some opportunities for taking care of this transformation. If we can do it over galactic scales, there's no reason why I can't do it over some smaller scales. Now, how you would do that, the details, the engineering details, that's a whole different issue. All I'm pointing out here is an opportunity. And I also want to say that's probably not the only missed opportunity. Remember when I started out with this, I said that the assumption is that space-time is infinitely smooth at the Fourier transform level. And the instant you say that, you wind up with horrendous digital modeling problem, essentially an unsolvable problem. So it kind of says that maybe we ought to look a little closer whether the digitization of the model is where we're getting some of the problems. Computers, entanglement, and observation. Now, and I should put a warning ahead of time. This is where I will be getting into a little bit of the more radical Terry approach. Terry being Terry being so radical, he thinks that a vacuum is a vacuum, which is a statement most people in the world would agree with. But I mean that in a strong sense that many of the things we think are solid physics are actually mathematical extrapolations based on infinite differentiability as being fundamental at all levels of reality. That's a tricky assumption if you apply that to the constraints of quantum mechanics. So all of these early guys assume that you have a complex phase space, a very complex phase space that mimics a classical computer. Now, right there, you want to be a little careful because you're assuming that you're trying to mimic a classical computer with quantum differential equations, with Schrodinger equations. The moment you say that, you've just said, I don't really want to use that. I want to use the ability to make it look like a computer. Well, yeah, but if you do that, guess what? It's going to start looking a lot more like a computer. So Poplavsky started this with a very good analysis of why there are two-state, you can reduce it down to two-state binary digits on whether you have a transition or not in any particular situation. It's great observation. Again, good paper. Manon points out that the phase space must be extremely elaborate. And this is where it starts getting dicey because Manon, in saying that, is essentially saying, how do we imitate a computer using these things? And it's presuming that the digital computer is the ideal go. Well, that 10 to the 42 kind of argues that maybe that's not the way reality does it. Feynman, same kind of thing. He says, take the same idea, lattice works with spins, which sounds a lot like a modern quantum computer. Again, marvelous paper, marvelous paper. And then you have the qubit as a generic two-level system. So again, everything is following along the same line of, let's make this thing as computer-like as we can. And the only serious divergence I've seen was Hopfield, where he talked about these useless or deleterious complications that are going on at the quantum level. So again, these are little molecules that look a lot like regular machines, but boy, they sure don't behave like machines in the details. They just figure, it's imagine like you have a machine that just automatically configures itself to the right way and says, oh, this is what I need to do, whoomp. And you look at it and you go like, how did it do that? And the honest answer is, even now, we don't really understand that. And that's an opportunity. There's a quantum computing opportunity right there. Understand, how does that silly methane molecule figure out how to do all these complicated things that we have so much trouble modeling? So do we have to recreate digital computers to access computing power? And I would say no. In fact, this is where I think we're missing opportunities. So let me give an example of a different way of thinking of an entanglement. Now there's actually, there's a lot of definitions of entanglement. Entanglement is non-locality, the idea that things have a relationship that ensures you will get certain probability distributions if you look at one part, even though the other part may be light years away. That's the essence of entanglement. It's saying that even if you can't send a signal, you can always find these correlations. So I want to give a little simple thought experiment. Imagine that you have a photon coming from, I don't know why I said high intensity. I would actually say a low intensity, but you have it from a source, and it goes to one of these little digital mirrors. These are marvelous devices. They use in projectors sometimes. And if you have all the mirrors flat, the wave bounces off, and you get no signal other than the fact that it bounced off a mirror, which is, by the way, a signal and is a form of a qubit because it's saying something new about that wave, about that photon. It says the photon reflected from this spot in space. So that's an interesting little correlation on that. Now, take those same mirrors, though, and do something a little different. You set half the mirrors to go one way, you set the other half to go in a different direction, being split. So the photon has a certain probability of going in the blue direction, or it has a certain probability of going in the brown direction. And those two directions are entangled, because if you find the photon here, it ain't going to be there. If you find the photon there, it's not going to be here. And this is, again, a beautiful, but this is entanglement going on at really a micromechanical level. And there's an interpretation issue about, are these things directly entangled with each other? Or what I would suggest is the radical thought is that the matter itself back here still has some kind of a role in this, that there's some kind of entanglement, that the level of details that these two guys get is powerfully dependent on the level of complexity back here. You see that same effect when I talked earlier about the galactic lens, because the details of the photon depend on an enormous number of bits and pieces going on at the same time. But you have to have that information stored somewhere. And the idea that one photon can store all of that information by itself kind of goes against the whole concept of information being proportional to energy. So what is your big energy source? Your big energy source is the mirror. And the idea that there's actually a more complex entanglement going on here, one in which these things have information that still corresponds back to these mirrors, kind of fits in with that idea that entanglement is more than just a simple relationship between these two blobs. It actually has a connection where it gets its complexity, where it can get an entire image from these mirrors down here. So again, a somewhat different way of looking at entanglement, in which you say, and somehow I managed to draw on the slide. I don't have any idea how I did that. Must have bumped something. Okay, probably the most radical slide that I have in this, but I can't not say this, and because if I don't point this out, you keep falling back into this many worlds model, and now I have a green line on every slide. I have I have no idea what that's all about. This is real engineering. You have a sun, you have a satellite. The satellite has a light sail. The light sail catches lights. It catches photons. They reflect off of it. Photons are not absorbed by that light sail. No matter what variation of QED you work with, you can't model it as an absorption. You fudge, you call it a potential. So you take the potential, which is really kind of a coverall term, and the potential coherently reflects the photon back in this way. Now, is this a real event? Of course it's a real event because you add momentum to the satellite. You push that satellite. In fact, you can get incredible velocities with enough photons. But just like the photon lens example, the Fourier transform, every photon has to contribute independently to this. So the photon wave function is quite real. It imparts momentum to that satellite. And once it does so, guess what? You also have a reduced, changed wave function right here. This wave function is now going in the opposite direction, has a different set of characteristics, and compared to the entire volume of the photon coming out from the sun, it is absolutely tiny. Now, what does that sound like? That sounds like wave collapse, because it is. It's the same thing. How did you get wave collapse? You had the wave function impart a bit of momentum without losing coherency. There's a whole set of terminology in physics for describing these different types of processes. But the point I want to point out is momentum transfers have an impact. They change the shape of the wave, in some cases dramatically, to what we would call a collapsed wave. We don't think of it as a collapsed wave because it's not atomic in scale, it's human in scale. But guess what? You can have wave collapses on different scales. This is also a scale-free process. So coherent reflection gives you that. What does that mean about the observer problem? It means that we're making it too complicated. It says that observation is nothing more than momentum, acceleration. If you exchange momentum, if you leave momentum, if you deposit a little bit of energy, you have an observation. This is completely backwards from the very high-level ideas of observation, because this means observation is going on everywhere all the time. And it's just exchanges of momentum, or what we would call acceleration. You can see that even in particle physics, and you see a picture of a charged particle going through a chamber, and you see the coiling effects from the magnetic field. That is because you're observing the particle almost continuously. When you send it through a bubble chamber, same thing. You're observing it almost continuing. Every time you do, it behaves like a particle. So it's sort of like chop, 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 chop. You get a particle. This is not wild hypothetical physics. This is how it works. It's all of this is a matter of interpretation. There's no ambiguity, and this is what happens. If you send a particle through a chamber full of light, it acts like a particle. If you do not do that, it does not behave like a particle. It's as simple as that. If you do not constantly observe it, every time it goes through a slit, every time it goes through a hole, it becomes a wave again. And this is one of the most common problems in YouTube videos, where they get the double slit experiment not just wrong, but terribly wrong. They'll show a particle going through a slit, and then it acts like a bullet and just goes zoop like this. No, no, that not only does that not work that way, you cannot get the double slit experiment to work if you have that kind of scenario. If you have particles big enough to go in a line like a bullet, they never interfere, ever, on either slit. Doesn't matter whether you open the slits. The only time the double slit experiment produces interference is when this particle turns into a wave again at this side. So you'll never get a little patch over here. And if you see a YouTube video that says that, it is just flat wrong. You cannot get interference and have those little two pools on this side. Instead, you get a big blur if you only have one slit open. So the point I'm getting at is that if you take the viewpoint that observation is the most common operation possible, acceleration due to forces, even at the atomic level, protons and electrons are constantly attracting each other, constantly accelerating each other, and thus are also constantly observing each other, which makes sense because they know where each other are. That's called an atom. The atom itself may then be delocalized, but the proton and electron, they're very happy with each other. Say, I know where you are, you know where I am. Why? Because they're constantly collapsing each other. The result of this kind of thinking, again, this is the more radical part I'm going and saying that observation is incredibly common and is nothing more than acceleration, exchanging momentum. Because when we exchange momentum pair, action, reaction, both know where the other is, that's observation. There's no complicated, certainly no intelligence involved in something like this. It's just ordinary physics, just interpreted a little bit differently. If this is true, there's no parallel computing universes at all. They're just not there. Every time this thing collapses, you have a possibility of something, but of a direction of that particle, but you don't have anything else. You don't have, there is no universal wave function in this kind of a universe at all. You have classical reality created by collapses of wave functions, and then you have empty space in between. So singular universe is all you get. And yet, we have all sorts of interesting behaviors. Now, if you use this model I'm talking about, bottom-up reality, where even just atoms are constantly, electrons and protons are constantly observing each other, then the Schrodinger cat problem becomes extremely simple. And it amounts to this. The cat either dies or it lives. It makes no difference. The fact you don't know about it is the only issue. So if you did know about it, you would have broken this wave function here. So there's a barrier that keeps you from poking at it too soon. But the cat doesn't care. It's going to live or it's going to die. It has enough complexity, has its own time, its own observation. Everything is just completely real, but it's inside of a bubble that's hidden. What then becomes very interesting, and this is where I say this might be a singular universe, but it's not a boring one, because where that cat can wind up is subject to interference. Now, how can that be? How can you have both of those going at the same time? Well, the answer is an interesting one. The answer is that you have to go to a different interpretation of space and time, that you have an idea that space and time are more like local implementations in which you create a special space-time continuum locally for anything like a spaceship that gets accelerated. And the level of fidelity of that instance of space-time is perfect. All particles behave the same, quantum physics behave the same, everything behaves the same within that bubble. But the point is that if you do careful accounting for the actual creation of these entities, of these accelerated entities, you find out that they have boundaries, they have metrical boundaries. And that puts a different spin on how we interpret space and time. And it comes into here because when you're talking about interference phenomena and some of these really interesting things that go on in quantum computing, you have to have some kind of a model that takes that into account. You can't have an infinite number of cats. You can have an infinite number of cat paths through space-time because you're creating the space-time. The uncertainty is on the space-time, not on the cat. How would it compute? If you have a singular universe, isn't that boring? Does that mean it's not going to have any computational power? No, not at all. In fact, it just gets much more interesting. I think this is a fascinating way of looking at the universe in which you say enormous numbers of entanglement are going on all the time via these bumping events, these ordinary mundane bumping events. Each time that happens, you're creating a new concept, a little local concept of space and time, right down to the particle level. And then you have collapses each time these bumps happen. But you also get entanglement between them. So that goes back to this idea of like, how can a single photon have all of this complexity, taking it down to a single point? Well, it goes right back to that issue. And they're saying that there's an entanglement with this enormous amount of matter that allows it to do that. That has possibilities for computation. because how you set up, for instance, on that mirror I showed earlier, how you set up the relationship of the images, how you impose an image on a single photon, also means you have a possibility for how to do things that you didn't think were possible computationally, such as the Shor algorithm. So a singular universe is not a boring universe. Right? It actually kind of boggles your mind a little bit when you start realizing space and time may not be as sacred as we thought, may not be as continuous as we thought. This is something you can see some of my previous presentations where I go in more detail. I have to throw this in just because I think it's important for understanding metrical systems and the possibilities of quantum computation. It's this. You can have entanglement. You can have non-classical, very real correlations between different components without breaking light speed. And I would say I'm a minority view on doing that, but I'm not the only one. A physicist named Asher Perez brought this out, that if you think of observing a particle, a paired particle at one point where Alice measures her spin, that somehow that transfers information to Bob's location. That does not work experimentally at all because there is nothing that you can detect at Bob's location that changes. You don't see the change until you get real information transferred at real light speed between those two locations. First time I ran across this, I just loved it. I go like, I don't understand what Perry's is saying, but I love it because he's making an important point that entanglement is not about changing things at a distance. It's about changing the nature of the information that's going on with this. Now, with my current terminology, I would say it's changing the nature of the space-time that you create when that new information gets there. Each bit of information modifies your local definition of space and time. And you're actually creating a slightly different bubble of space-time. If you throw away this idea that space-time is uniform and it's kind of like a magical substrate in which everything happens, and replace it with one in which matter creates space-time on a case-by-case basis, boy, you get a lot of options for understanding weird effects that currently are very difficult to explain. But also in those options, you get opportunities for saying, how do we approach computation differently? Wrap up. If you're thinking about quantum computation, I encourage you to think holographically. Holographically is a powerful, powerful mechanism, and it's not really that complicated. Here's another one of my attempts at a simple diagram. You got a pond, you throw two rocks in it, the rocks make waves. If you freeze those waves, you have a really hard frost coming all of a sudden, and the waves get frozen. You can't see the particles anymore, they sank to the bottom. But guess what? You can look at that pond and tell exactly where the particles went in. There was a particle here, there's a particle there. And why is that? Because you're using a hologram. You're using a Fourier transform, which is a hologram. The wave functions encodes the location of the two particles, even though they overlap. So each little region here gets enough information that it can say, well, yeah, there's a rock approximately there and approximately there. So the smaller the area, the less information you get. The more of the area, the more information you get. Oh, by the way, surprise, large language models, they're holographic. If you look at the way they work, if you get too small of a little slice of the way they store the data, you get nonsense, you get chaos, you get hallucinations. If you have a query that accesses enough of the full content, the image starts being sharper and you get you don't get thinking, you get a copy of someone's paper. So LLMs are an amazing thing. You know, they are large language models. They're databases. They're not intelligences, but they're good at retrieving. They're very good at retrieving things because they use a holographic principle with that. That's just Terry saying that I can't quote a paper for you. In fact, I keep wanting to, if I get around to it, I'm going to write a paper about how Hopfield had a holographic insight when he did his paper, but I just haven't gotten time for it yet. Fourier duality is holographic. Because if you think only in terms of position in space, you're going to wind up with a circuit and a fully fixed position-based XYZ interpretation, and you're going to get explosions of computation costs, just unbelievable explosions of computation costs. If you think more broadly and allow both of these to come into play, I would argue that you get some of the access to this phenomenal power of photon quantum Fourier transforms. Examples, Lenzing repetition or waves, diffraction. Anytime you repeat things with a wave going over it, you wind up accessing this different kind of space, this momentum interpretation. Incidentally, there is a common interpretation in physics going around these days about the holographic duality of the universe. Please note, I am not talking about that duality. That duality is based on what I would consider a very shaky interpretation of bits as being the surfaces of black holes. And Tahouf, a great guy. Tahouf is a great guy and a great thinker, but I can't agree with him that because you can't just magically make the surface of a black hole into a bit. Bits are not made that way. Bits are more complicated than that. But the duality I'm talking about is the one that's been known since the 1920s, which is the dual wave function, position momentum wave function duality. And it's a broken duality because we see the momentum space only fragmented, whereas the position space is enormous. And I don't think that's a coincidence. I think that fracturing of a symmetry between the two spaces is a real factor in why we exist at all. So if you're trying to do quantum computation, try to think a little more broadly and whether you can use tools like lensing. Can you do a complicated lensing set? Can you do repetition? Can you encode images onto single photons? You want to think a little creative. Can you use photon transformations to take care of things? Stop thinking about quantum as cold only. It's not true. This always amazes me. I mean, the fact that you're sitting in a chair you have volume is due to quantum mechanical Pauli exclusion. Otherwise, you just turn into a black hole in a few milliseconds. So that's very quantum. Colors of opals, those are a very quantum effect. You have light waves going over a large area, reflecting and showing the structure of that opal, which is actually a form of computation. You're getting a great deal of information about the structure of that opal by reflecting light off of it. And again, this goes back to the idea, could you get information? Could you get computation out of that? Probably so. The use of the Shor algorithm, the Coppersmith algorithm, says that there's some kind of connection. The fact you're reading this text, the lens in your eye is doing Fourier transforms on individual photons, not on the giant light. I mean, if you're an owl, you can see photons coming in one at a time. Humans actually can detect individual photons statistically. They don't, they just sort of like, they're kind of guessing, but they've done studies where even humans can detect individual photons. There's was some recent news about something called super radiance, which is really just a different version of a lasing effect. Lasers have been around for a long time. But lasers are also very quantum effects. They also play games with space and time because you have the entire volume of the lasing medium winds up contributing to these individual photons. Now, the work that was here was that, and where it got some attention, is they showed that this happens in the molecules that the amino acids that form microtubules, which are what Penrose proposed for human quantum computing sort of thing. So this was a paper, when I read that, I go like, oops, because I had been down on Penrose's idea for decades, including occasionally exchanging emails with him or saying like, have you try something else? This doesn't work. So and I saw this, I go like, oh crap, this is, it shows that you can have room temperature quantum effects of non-trivial complexity, including suppression and emission of photons of different energies. Now, whether their particular work has anything to do with the brain, yet to be proven. They were working, I think, in ultraviolet. Brain obviously does not. But they certainly showed the principle, and they showed an extraordinary connection to the same amino acids that are being used in some of the structural repetitious parts of the brain. Repetition is important. When you have repetition, it tends to encourage quantum momentum space effects. Ordinary mirrors are incredibly quantum because you have electrons that have gone over into momentum space. Momentum space is so real that electrons can sit there. They can live there. They can get very hot there. And when you look at a mirror, a silver mirror, the electrons that are reflecting that light are hot enough to kill you if they suddenly fell back to ground state. So this is not just some abstract issue. They have to get a lot of energy in order to go to the surface of the Fermi layer where it gives this reflective effect. So there's a huge number of very quantum effects, some of which are almost certainly relevant to quantum computing. But we keep thinking cold only because we're focusing so much on individual atoms where you have the most precarious form of quantum mechanics, whereas you get these massive versions of it that we probably ought to be exploring a little more. Don't digitize everything. If this whole assumption, this sequence of these really sharp people with very good intentions, but always just building and building and building on this assumption that, wow, computers are neat, because that's part of what's going on here. Computers are really neat, so let's make physics into a bunch of computers. And there's good arguments that's not really the way it works, because you wind up with these insane estimates of consuming all the energy on Earth just to mimic one molecule. So nature's got a better way to do it. We should pay more attention to how nature is doing it. Um, and unfortunately, this goes back to the assumption, which is much beloved, and still you have to point it out. When you say smooth differential equations are the foundation of everything, you will get into computational trouble every time, because a smooth continuum is an infinitely dense digital problem, always. Never fails. Usually they'll put a qualifier and say, well, maybe space is digital. But really, that's kind of a cop-out, because there's no evidence that space is digital in that sense. There's no evidence that space is a matrix of a precisely defined set of points. It is true that we can model it well with that, but that's the same thing as proof saying that space is that way. And those same models also have some tremendous difficulties when you get to things like density of space. Quantum world is not as energy inefficient as what happens when we assume reality is digital. So one of the focus points I think we need on more advanced quantum computing is efficiency. Biochemistry is extremely efficient. How does it do that at the molecular level? I'm not talking about DNA computing. I'm talking about how the individual molecules, how the enzymes kind of look around their environment and say, yeah, I ought to head over here. Something quantum is going on with that. It's not statistically working like a regular machine. And we don't have enough understanding of that. History of qubits begins with digitizing a computer continuum. Don't do that. That is not a good start, because even with a simple analysis, you say this is going to wind up at infinity. And the world does not wind up at infinity. So instead of making the world infinite, full of infinite infinities of infinities, which we don't observe, let's just assume the world does it a little bit differently, and that might be a good starting point. And yes, that means that you have to abandon extremely dear concepts like, everything is infinitely continuum differential. Infinite differentiability is just a much beloved concept in mathematics. But that doesn't mean it's a good model for the physical world, which definitely does not have that level of continuity. Uh, we need to abandon that intensely digital background. Look at some other possibilities, especially momentum wave functions and these large room temperature things. I point out particularly photon-based quantum Fourier transforms, I think, are an opportunity. And by the way, those are also an opportunity. I brought this out before. Those are an opportunity for people who love LLMs, which I'm not a big LLM lover because their databases posing as AIs. But if you want to make a more efficient LLM, large language model, the idea of using photon-based Fourier transforms there, if you convert them into a Fourier perspective access mechanism, which I think is a much better model than matrix multiplication for what they're doing, much more energy efficient, then there's some possibilities there too. Holographic lesson. The idea that holography is a good way of thinking of some of this, especially if we can get some insights from molecular biochemistry. I think that could open up some novel quantum computing doors. So I guess my wrap up is just to say that I think there's a lot more potential in quantum computing than we realize. And that's a strange thing to say because so much money has been spent on qubit approaches, and you get progress with the qubit approaches. But I think we need to broaden the net a bit and look at a broader range of physics and say, what could we do if we don't start with methane molecule modeling, which is which is where a lot of this came from, is how do we model a methane molecule? I find that hilarious because that's a very coincidental kind of way to start off a whole field. And yet there's a lot of roots of quantum computing in that simple statement. Is how do I model a methane molecule and why is it so hard? And with that, I am wrapped up and let's go to questions and answers.
Uh, I noticed Marco. Marco has a lot of comments. So Marco, can you unmute yourself and ask all your questions online? So maybe Marco is not around anymore. So I noticed another long question. Okay, the question is, a qubit must be artificially fabricated, unstable, and demand cryogenesis with heavy error correction, and if photons, while fast, are hard to make indirect and mostly solve nature problems, then why not use molecule nature ready-made quantum computers inherently encoding billions of states, orbital vibrant conformations directly interacting, robust to noise, and operating at room temperature without costly infrastructure, programmable via a Python-like DSL compiled into laser pulse, DNA triggers, and electrolyte signals. Isn't it time to build a hybrid molecular quantum computer, a biological quantum brain that's robust, energy efficient, and capable of real-time protein simulation, post-quantum krypton analysis, and novel material discoveries?
That was a long question. um,
Yes.
the gist of it, I think I'm agreeing with the gist of it, saying that, yeah, I think we can do some much better versions of quantum computing, and that bioinspiration is definitely a source for that. The trouble is we still don't have the experimental data to understand what is going on in some of this. There's no experimental proof that an actual biological brain is using quantum computing, and it's very important to emphasize that. But there is extremely interesting evidence that such phenomena can exist. And like I say, I was a convert. I mean, I disagreed with Penrose for decades, literally decades, about the idea of whether, not that my opinion mattered, but just point was I just read his stuff and said, no, this is wrong. This is not how quantum systems work. But you look at these network type applications, especially with a lot of repetition, all of a sudden you go like, whoa, wait a minute here. This is you can't exclude that possibility. So I think I like the drift of where the question is going, but would be a lot of research involved in trying to make these things into actual working devices because we don't understand, especially the biological side of that. Those molecules, what Hopfield did back in 1974, I wish he had pursued that more. I wish that someone would pursue that more and say, how does this collage of mechanisms, and I'm sure there's some work out there, but how does this collage of mechanisms produce this result, and which parts of that are quantum? Especially that last question, which parts of this are actually quantum interactions that biology is leveraging? So I think if we had research on some of these issues, it would be very helpful for trying to do that. but I do think there's potential there. And I don't think that the massively cold approach is the only approach that's appropriate. That's the
Thank you.
best I can do for that long question for right now.
Seems like Ron unmute. Ron, do you have a question?
Thank
I
you,
notice Ron
Helen.
has a question.
Thank you, Helen. Thanks, Terry. This has been such an intense presentation. It brings some
Well, thank you.
humanity to some of these features, some of these abstract ideas. I really enjoyed it. On your slide 4, you're talking about lattice work with 10 to the 42 points. Is there any known visualization of what that looks like or at a macro level? I mean, obviously you can't visualize 10 to
Yeah,
the 40.
they're using a Hilbert space. They're using just conventional three-dimensional space using complex vectors, but still it's basically a three-dimensional space, and just elaborating that with more and more dimensions. So you see this same discussion in discussions about how large language models work, the transformer model. You can always break it down into individual pieces where it looks just like the figure where I showed the projections of the shadows, the dot products. It all turns into that. So the fact that you have 42 dimensions doesn't really matter. It's just the number of points is what matters. But the individual points you project across these different dimensions, and they're at different angles. So the figure, and I forget which figure it was, but the one with the several examples of what a qubit looks like,
It's
showing a
actually
bit.
slide 11. I was going to ask
Yeah,
a
slide
question.
11, but
I
that
was going
is,
to ask a question about that too. Did these evolve into the block sphere, or did that come from someplace else?
I'm sorry, I couldn't quite hear you.
Did these angle diagrams on your slide 11 evolve into the block sphere, or did that come from someplace else?
Did they evolve into the
Block sphere.
blogosphere?
Block.
Those figures are just ones, and I entirely created on my own.
Okay.
They're just showing the representation. I used to do a lot of work on the spin representations, and spin 1/2 is fascinating because it's sub 3D. The fact that those are 90-degree angle, it turns into our space as a 180-degree angle. So you actually have to kind of stretch those angles out, and then they form what we think of as up and then down. But in the case of spin 1/2 is very, very strange, very strange. And also that strangeness is important, how reality seems to work. So, but you get that, the diagrams just show the orthogonality of up and down. But in real physical space, the orthogonality bends like this, and you get that weird spin 1/2 situation. So I just love the bizarreness of that, about how it works. But the figures are very, in terms of using the dot products, that really is how you understand both transformer models and large language models, the pseudo orthogonality there, the idea that you have a little bit of this and a little bit of that, remarkably holographic and multidimensional there too. But it all turns into these little dot products. You know, you lean it over and you look to see how the shadow, then you square that shadow. That's the probability function. That's just all through quantum mechanics, and allows you to understand the dynamics of even a 42-dimensional space, because you can always just look at 2 dimensions. You know, just subset it. You don't want to think, oh, it's too many dimensions. Well, you don't have to think of all those dimensions. You just think of a small number, a small set, and look at each individual point. And then you can rotate the entire structure around to get the other dimensions to where you can look at those. So there's ways to do that, and that diagram gives you an idea of that. But again, that is, I think there were some diagrams I could have copied somewhere, maybe from Feynman, but no, I just tinkered with
Actually,
those ones to get them
you
where I
just
like.
explained the block, BLOCH sphere.
Oh, the blocks. I've got a whole different thing about the block sphere.
Okay.
I would refer you to a previous presentation which I rag on the block sphere, because oh my gosh, that thing is so asymmetric. It's just incredibly asymmetric. because of its real-time continuum assumptions. And I have some, I would prefer to use a quaternion representation, which doesn't have the asymmetry. But I think that's, I've got a couple papers on that. I don't think that's a widely used technique. The block sphere works. I'm not saying it doesn't work. I'm just saying the fundamental representation has an infinity of digits at the top, one digit at the bottom, and then you have this projection asymmetry that's created on that. The diagrams I show are an easier way to understand those relationships. And yes, I would say that the shadow relationships are an easier way to understand. And again, that's not new work. This is goodness, Feynman goes in great detail about the understanding the dot products. And also there's a good YouTube video about large language models where he does a good job of running through that same example, talking about how the large language model comes up with a particular identification of a person. Oh gosh, I can't remember the name of the YouTube channel. So there's a few sources we can get it. The block sphere adds so much complexity if you dig into it that is not there. And that troubles me about any mathematical technique that adds enormous complexity that is not there, because a qubit is not that kind of structure. It is not a sphere. It is not infinitely dense at one end and zero at the other. The block sphere is so complex that I talked to one fellow once who was seriously looking into imposing general relativity space curvature on top of the block sphere surface. And it's not that you can't do that. It's just that you're imposing that kind of complexity onto something that is entirely a mathematical construct. And a simple qubit is always just a couple dot products. It's never anything more than that. So yeah, back in that, those diagrams will give you the gist of a qubit, I think, a lot more visually easily than trying to go through the block sphere details. The block sphere are a handy way to transform it into a mathematical notation. It's only at the conceptual level that I object and say, like, yeah, don't take that too seriously. Don't apply general relativity to a non-existent space. It might make a good paper, but it's not going to give you anything terribly useful.
I appreciate that, and I agree with you. The angle diagrams are easier to understand. They don't.
Okay, well, thank you. Again,
the block sphere has that squaring function, which you have to explain to people. That's not really it's really 90 degrees. It's not 180 degrees, and all that goofy stuff. So I kind of agree with what you're talking about.
Orthogonality is just a marvelous concept in quantum mechanics, and like I say, I love the electron, the half-spin particles, just because they break ordinary orthogonality. And I just keep going. I'll go back to one more time, but 90 degrees, that's what's going on. And yet, somehow those silly fermions creak it out this way. And I don't see it as a casual comment. The fact that they are so persistent somehow is related to that property. And the fact they're able to carry information is related to that property. Because if you go to the next things, the one spin particles, the bosons, they don't have that property. And also by themselves, they're not good at storing information. They just kind of go out everywhere. So there's something really interesting about that quirky little half spin that you get in fermions. So.
Thank you. Thank you so much.
Thank you. Other questions?
Yes, I saw a question from Dev that how can you explain the following without quantum computing or quantum? 1. BEC, Bose-Einstein condensation experimentally verified. Question 2. Detection of gravitational wave with quantum squeeze states. Question 3. Hundreds of experiments of Bell inequality violation over the world. Question 4. Recently Bell inequality violations experiment. Event violates the upper limit of speed of light. I will spend some research paper also.
Interesting set of questions. Okay. The first one I think was about Bose condensates.
Yes, it's on the chat.
So what was the question about Bose condensates though?
Okay, maybe ask one question at that, or maybe is that around?
Oh yeah, okay. I think I've seen it.
Unmute.
Bose condensation. Oh yeah, Bose-Einstein condensates absolutely are experimentally verified. Those are a marvelous effect with that, and they deal very much with momentum space. I mean that's what a Bose condensate is particles going into a momentum state superposition, where the idea of a singular atom in ordinary space no longer exists. A Bose condensate, in many ways, is a gigantic ball, is a gigantic atom composed of many atoms all spaced in the same place. And they can do that because they're in momentum space. They're no longer in our regular XYZ space in a fashion that you can really understand. Of course, that's true for a mirror too. The electrons that reflect light in a mirror also are in a space, a Fermi sea in that case, that is not something you can explain by ordinary physics, but they also provide things like strength of metals. The fact you think of it this way, if the electron stretched out over this huge chunk of steel, guess what? It makes it harder for the steel to break because the electron has to relocate itself. The Bose condensates were found, oh, I remember when they first found those. Arguably, helium-2 was always a Bose condensate, so they kind of exclude that one because, you got to have your spectacular discovery. And if you say that helium-2 was the first Bose condensate, you don't get as much traction. But the Bose condensates they're just beautiful. I mean, have you seen pictures of them? They're like shiny steel balls that reflect the light from that. And it's just a marvelous example of how these things play strange tricks with our concepts of how particles occupy space and time. So I certainly agree with that. Second question was?
Detection of gravitational wave with quantum squeeze states.
Quantum squeeze states. In fact, I almost put in a paper reference to a quantum squeeze state. I'm just going to pass on that one because I haven't. I looked at this quantum squeeze states once in detail, and it's a beautiful paper, and beautiful work. But I'd have to go back and refresh on that. I didn't take a look at that. So I certainly agree with the existence of quantum squeeze states. They obey quantum mechanics. They don't violate anything, but they certainly show you how you can do some interesting manipulations of the quantum states and make them do things that are both useful and interesting. Third question?
Third question. Hundreds of experiments of Bell inequality violations all over the world.
Is Bell's inequality proven to be violated? Absolutely. Yeah, yes. Quantum entanglement, Bell's inequality. I mean, when Bell proposed that, he wanted to prove Einstein right, and which is one of the deepest ironies about that. But he acknowledged that that's not where it went. It showed he showed a way to experimentally show the non-classicality of these relationships, and he succeeded in doing so. He didn't mean to. Now, the question I said when I said that you don't need to violate the speed of light, I also meant that seriously. You can have Bell's inequality violations without violating the speed of light. And this to me is an extremely important point. People have gotten remarkably casual about violating the speed of light when it comes to metrical frameworks. So you accelerate a spaceship, you create a metrical framework, and then you instantly apply it to the entire universe. No, it doesn't work that way. The rulers in the rest of the universe didn't change. They don't give a hoot about what you did. They don't even know that you did it. You're isolated from them. It's going to take the speed of light before they even know that you accelerated. The rest of the universe don't care. So, and yet when we go to these metrical frameworks, people just magically and unconsciously use the mathematical framework to violate the speed of light. And we need to stop doing that because you can't get at the deeper nature of space and time if you're constantly using frameworks that don't exist. So I would say Bell's inequality absolutely has been verified to be a real issue. But also, if you put the flexibility of saying that space-time itself has some variability, you get a whole different way of approaching that and trying to figure out what's going on. And it doesn't involve sending signals fast as speed of light. I'm really big on speed of light, but I'm also really big on Bell's inequality being violated. I love the conjunction of those two. I think the fact that those two both exist and both have very good experimental backing is exactly why we should look more carefully and say, what is going on there? So, and was there a fourth question?
The fourth question is, recently Bell inequality violations experiment even violate the upper limits of light.
Well, I think I just answered that. I said, no, none of this violates the speed of light. You never have a case in which you can show an action at a distant point. All you can ever show are weird correlations when you do get information. And those are not the same statement. That is not the same statement. Saying that you change something's speed of light is our intuition using infinitely metrical spaces with infinite extent for free. But if you qualify that and say, wait a minute, maybe my metrical space has limits also, then suddenly you have new opportunities for explaining how both of those can be true.
Thank you.
Thank you.
And I got a question from Lindell Aaron. Where is the best place to learn about methane modeling? Perhaps in a lecture for beginners?
About which kind of modeling?
Methane modeling. Methane modeling.
Oh, methane. Oh, I've got those listed, those papers there, and I think I have references on the slides, and I think I have links too, so you can find those papers. I will try to put a couple of those. Two of them were in German, one was in both German and Russian, and I've got a translation of one of them, and I'll put that up on my website. So I will add that in so that those are more available. So in fact, I almost did the one paper on that, but you can find the references and you can use Google Translate to start looking at those. But yeah, fascinating little history there, and of which I was completely unaware until I started going into other languages and realized there's more history to this than I thought. So thanks.
And his other question is, have you encountered interpretations that describe quantum states as a rotation at discrete frequency?
I'm not sure about the discrete frequency part, but certainly quantum states as rotations. I think I even mentioned that in some of the slides. Absolutely, you know, that one set of diagrams where I show the meaning of a qubit. Those are rotations. I mean, those are, you know, you're literally rotating that one thing. When you, I am getting, can you hear me? I'm getting it. So rotation is, yeah. It's all of these things, and they're part of the modeling. So, anyone else?
Harry's audio is breaking up. I think you're back.
My apologies. Can you hear me now?
Yes.
Yes.
Yes. I'm sorry. I'm going to go to a wired connection next time I have one of these. I think I can set it up. So apologies for that.
One more question. In domain of quantum mechanics, do you define a single universe as a set of objects?
I would define the single universe as a set of persistent quantum properties that are capable of regrouping in extremely complex ways, but often with very strong patterns. And those strong patterns lead to the emergence of what we think of as information. So I would say it's a singular unit, but it's not a singular universe of particles. I think that's a misconception. Because like the slides where I said, every instance where you actually talk about a particle, and this is not wild guessing or something. This is the actual experimental reality. You cannot see a particle. That's why we have gigantic accelerators, just to make them seem smaller, because you have to put that much energy in them just to make them seem smaller. Well, asymptotic limits are not the same thing as reality. If you say everything's a particle, you've instantly invoked infinite energy. And then you wonder why you have a vacuum density problem. Well, you know, there you go. If you invoke infinite energy, you get infinite energy. So we should be a little more cautious on even terms like particles and waves. The Copenhagen interpretation, which is still my favorite interpretation, by the way, nonetheless is an extremum interpretation. You have a bunch of people with a classical background. They're going into a problem where everything looks weird, really weird. So what do? They break it into two parts. They break it into point-like particles, and wave-like thingies, both of which are classical. So what it was, Copenhagen interpretation is a way of using classical, extremely classical terminology, concepts, mathematics, equations to do a pretty good job of analyzing this weird new quantum world. Now, what I'm suggesting is you want to get away from the extreme. There has to be some new quantum interpretation that never says particle and never says wave except as emergent properties. And that to me is a fascinating little world. And it has to do with this idea that space-time itself is a little more wonky than we think it is. But you get emergences of wave-like things up to a limit. You get emergences of particle-like things up to a limit, but neither is fundamental. The actual action is going on in a deeper set of constraints where everything is very highly conserved. Conservation is really big in this. Conservation of the energy, conservation of certain properties like charge. You can have pair creation, but you can't just do away with things. All of that generates these behaviors that we call waves and particles. So again, that's Terry on the radical side, but in some ways it's not that radical because that is what we observe. We never see perfect waves. We never see perfect wave states. That's acknowledged. Every good physics quantum textbook will tell you that. There's no such thing as a perfect momentum state. There's no such thing as a perfect point state. That's nothing debatable about that. But we don't do it at the model level. We don't go down and say, yeah, we need to start somewhere else. And what I would suggest is start with absolute conservation of properties, and then these other things emerge through extremely high levels of mutual observation, which is just pumping. And that's radical Terry saying stuff like that, but also very closely tied to what we observe. So it's not based on wild speculation. It's just saying like you bump something and they know each other's location. And also, if it's a quantum wave, it always collapses, always, without exception. How is that different from observation? So, other questions?
Helen, you're on mute. She's reading. Helen, you're on mute.
I'm sorry. Yeah, there's another question. Not question is a comment from Marco. Your Fourier model is missing the tau form that would be needed. The probability amplitude results from a probability density function. The probability of an instantaneous instance is zero. Think of trying to crush a wave with more waves. It's a comment.
It's a it's an interesting comment. I'll go back and you're going to send out the comments later, right, Helen?
Sure.
So,
Let me paste the comment again.
okay.
Yes, it's in the latest.
Yeah, I certainly didn't intend to give a complete model of Fourier transforms with that. That was just like some very basics on it. So, and there's gets really interesting when you get into some of the quantum aspects of it.
There's one more question. According to your knowledge, which quantum laws or equation can we base our modeling?
Well, I think I'm putting on Terry's radical hat here again. The points that I would emphasize, okay, first of all, I dismiss the multi-world. I could give you so many reasons why I dismiss the multi-world approach, even though it's been very influential. And it's not that you can't predict things with it. Don't get me wrong. There's a lot of things you can do in quantum mechanics where you can predict things. But some of the key predictions of many world just haven't panned out. I mean, the infinite computation from 15 qubits, come on, it didn't happen. It didn't happen because you didn't have real universes. You only had shadow projections of our universe, and those are more limited than that. So I would say, don't, go to a singular universe. Uh, Conservation laws are so important. If you have this idea that conservation of things like charge is so absolute that one charge applies, conservation applies to the entire universe, to every other particle in some sense, feels the existence of that one particle or that one pair, and you can't get rid of it. They can't just disappear. You can have pair conservation. We have pairs are created and you have pairs collapse, but the total charge is extremely persistent. If you have that kind of focus on conservation laws, get away from the idea that empty space is metrical, because you can't measure empty space without matter. Just, you can't. It becomes a nonsensical statement the instant you say it. Well, as this empty space has the following properties, said, how do you measure those properties? Well, I hit it with an electron in a gamma ray. Well, didn't you just add energy and matter? Yes, I did, but so what? Well, because it's not empty anymore. We only see metrics where we see matter and energy because that's the only thing we can observe. And that fits right in with Einstein's thing that empty space looks the same to all observers because it's empty. If you put a quantum foam in it, and people don't talk about this. I don't understand why people don't talk about this. If you put a quantum Planck foam into space, you have made it locked into one inertial frame, period. You cannot create a Planck foam that is universal for all observers. It's not possible because you have these fluctuations that have an intensity range that are locked into some kind of a central point that says, oh, here's where they are minimized. And I don't understand why people talk about Planck foams as if there's some kind of independent concept that works for empty space. They don't. They only work for a particular metrical frame, which is not a coincidence, because when you get into issues of like the Feynman integrals for different particles, those are frame dependent. And once you get into a frame, you can start talking about stuff like that. You can start talking about particle pairs forming. You can start talking about the foaming of space in that one frame. But you can't talk about it and generalize it to some other frame. And I may have drifted because I don't even remember if I answered the question. So hopefully I answered the question. I'm not sure.
Actually, here's another comment. It's a comment. Look at the Barry pseudo rotation. That's where the methane model came from. The issue is that the CH4 plus H plus equal to CH5 plus with an extreme low rotation barrier between square-based pyramidal and trigonal by pyramidal geometrics, that is an interaction between C4V dash divided by D3H groups whose dipole moments would be extremely useful to exchange. Let me post the whole comment on the chat.
Post the comment. It's an interesting comment. There's no way, especially I do not do well equations verbally. So trying to put that together in my head, I have no idea. But it's an interesting comment. I look forward to looking at the question.
And I
Any other?
noticed some people have good comments. Thank you, Terry. Really interesting presentation. More, please. And
Oh,
yes, we want more talks.
thank you. I will be giving a talk on I'm sorry, who?
Can I follow up with a forward-looking question?
Oh, sure.
So, based on what I've heard you present today, I'm wondering what are your thoughts on building a quantum computer, possibly built with a large array of devices that are both single photon sources and single photon detectors, and
I think,
leveraging this concept that you said they transmit like holographic information.
yeah. Yeah, I do actually think there is a high level of potential for getting a better implementation of quantum computing using a structure like that. hybrid architectures that make use of it's not exactly analog. I'm not sure what to call it. Holographic still seems the best thing. Composite holographic digital quantum computing to me seems like a high potential area for some research. Incidentally, I should mention I have a background of getting funding for people to do research. I love that background. I love doing it. I love seeing when companies that I helped got big and made, I love people making bucks as long as they don't abuse it and try to undermine democracy. I'm not that I'm referring to anybody in particular, but when people use an idea and work on it and go out and produce a new product, I just love that. And that's where that's what I enjoy doing it. I am not myself one who particularly enjoys saying like, oh, I'm going to make a lot of money doing this. But I love it when other people do that. That's one of the reasons why I've enjoyed giving people ideas. So when I casually make a comment saying like, I think there's a high potential of doing a quantum computer that is based on a hybrid holographic approach. A lot of people say, "Oh, I think I'm going to go out and do that." Well, if you want to, if you have an idea and you want to elaborate on that, please feel free, go at it, because I like the idea of people being excited and looking, exploring some new idea. And I do think that's one of them. And by the way, that particular idea also applies for the LLM community, large language model community, because their systems are holographic and they don't know it. Some of them are kind of figuring it out. The math is already there. The pseudo-dimensionality is already there. Actually, it's all the mathematical equivalences are already there. The dot products, the whole schmear. But they don't think of it that way. They think of it as matrix multiplications. And holography is not matrix multiplications. So that's one of the reasons why they have such a high cost. So I put out, Helen, I think it was one of the earliest presentations I gave. I gave out 3 suggestions. One of them was the one that DeepSeek did. Either I predicted it or they did it. I don't know which. I don't care. But that was the one that caused a huge stock market dip when they got enormous gains in efficiency by predefining the holographic pseudo dimensions. So the other 2 suggestions are to go this actual use of real holography, I think would give far larger collapses in the cost of doing a large language model. So it's not just quantum computing. This applies in multiple areas. I think holographic based computing has potential, but it also needs a lot of work. We still don't understand some of the encoding principles, if nothing else. Coppersmith is a good starting point. I mean, he says, he shows how that can do some real impact by having a fast quantum Fourier transform, which is what he has, but not necessarily one done with photons. So yeah, there's potential there. And I like talking about it because I like to encourage people to just think it through, see if you can come up with an idea, see if you can make your own company. I don't care. I have zero interest in creating some company. That's not where I get my excitement out of life. Solving problems, encouraging people to do things. That's fun. That's fun. So I think it's great when people can come up with a new product.
Well, thank you again. You have certainly planted some seeds for thought on my end. I had a crazy idea about how to build a quantum computer a while ago, and after what I've seen today, it may not be that crazy. It was based on photons, but
good for you, Ron, and I hope and good luck with that. There is, like I say, there is more literature out there than you might expect. I throw out some wild ideas, but there's quite a few papers. In fact, give me a second, I'm going to take over the share again. And now, if I told you that picture is the view out in my backyard, would you believe me? I hope not.
You must be in an
okay. Here's some of my quantum computing papers, just to give an example real quick. Can people see this? Yes. Okay. Single particle act as a quantum computer, exploring the boundary of quantum correlations with time domain, practical framework for assessing performance, high-dimensional multipartite entanglement, ultraviolet superradiance. There's interesting papers out there. In fact, actually, I think, yes, I have those papers up. Okay, see, here's one. Oh, and the I'm having trouble accessing the papers because of that so anyway, here's just a few examples, some of these papers. The thing I'm doing in a paper, and this is the Google effect. Google was the original Google paper on the page algorithm was one of like hundreds of good papers. And I remember thinking that at the time. It says, it wasn't that paper was more insightful or more radical than a lot of others. It was that he had some people that saw the advantages and were able to run with it. And often that's true for a lot of these things, is that you can take, I don't doubt that any one of these papers I'm showing here, some of them have really high potential for doing something really good. But the trick is to get that point where somebody just understands and says, oh, here's where I'm inspired. Here's what I need to do. Here's what's going on. And that's the harder part. And you got to kind of get some enthusiasm. Of course, the super radiance, I think that is one of the most interesting ones, because it just completely undercuts our usual perception about quantum mechanics being only a cold thing. No, it's not. And this shows that strange things are possible. But how can you get information processing out of that? Nobody knows. So if somebody does this and come up with an idea and say, oh, I think I see how to do it, there's a product potential right there, a research potential, whichever route you might want to go. So is there potential there? I think that one's got a high potential. Super radiance as a computational mechanism is intriguing and also not understood at all. So lots of interesting papers out there. And I say there's just a sampling of a few of them there. So I'll leave it at that. Any other questions?
Oh, yes, yes. Lindell asks, how can we connect with you to discuss quantum computer architectures? Best way to connect you? What was the best way to connect with you?
You can, LinkedIn is a good way to contact me on that. Yeah, my email address is extremely common.
May I ask a question?
Sure.
Yes.
You mentioned some 15 minutes ago or more about biology and quantum computers. And some years ago, I heard somebody talking about bacteria-run computer instead of the hardware that we are using these days. And of course, the quantum computer idea sounds very attractive here to look at. Have you heard anything about that?
I think I've seen some mention of bacteria from a computational viewpoint. I would certainly agree with the statement, because the amount of environmental interaction that a single bacterium has to do in order to survive in an often hostile environment is mind-boggling. And we don't perceive that because we're so used to bacteria being everywhere. And it's a
Even
misconception.
biofilm,
What's that?
the biofilm expansion
Yes.
of helium looks very calculated.
Yeah. Yes. Biofilms, if you look at the details of a biofilm formation by bacteria, you think of bacteria as a single little organism, it's all by itself. First of all, that's not true. fact, almost most brands of bacteria, not all of them, I'm sure there's some exceptions, have programmed into them remarkably complex behaviors that allow them to behave as colonies, which are more effective at attacking or eating whatever their food source is. And this goes in with the computer model again. It says to think that the set of reactions inside of a bacteria is trivial and is just eat, reproduce, and even the reproduction. Have you ever tried to split yourself into two people? It's not easy to do. So it's quite tricky. Have you ever tried to get your TV screen?
Humorous. That's very humorous. Okay. Great ideas. I hear it from you all the time. And I have to thank you for everything.
Well, thank you. I appreciate
All
that.
the best. Thank you. Cheers. Okay, I will be looking at the papers you listed. Are you on papers or just papers in quantum computing?
Oh no, those are just papers I collected. I'm not an author in any of those papers. So if you might see my stuff, just go to my website and you can see my various ramblings. I'm much more in a exploration mode, although it's coming to some points like on the I'm literally trying to rewrite. That's not presumptuous. I'm literally trying to rewrite special relativity, and boy, do I have a good little lock hold on it right now. This tilted block method is so much more predictive than the Minkowski space. So I've got my little pet projects, and I may put in some papers, but mostly those, all those were collected papers. So, but there's good papers out there. You always got to do a literature research. Always.
Fantastic. Thank you so much.
Okay, thank you.
And Bill has a comment. If you ever know someone who comes down with a MRSA infection, this will save their life. It's a comment.
Good recommendation, Bill. That's a tough one to treat. So options are. I once had an infection. They were going to put a PICC line in me. They were already pumping vancomycin into me, and because I had tried it before for a skin infection, I kind of pleaded with the doctor. Said, "Could I try these two oral antibiotics in one combination instead?" And an infection that had been going on for weeks, for months, cleared up in 1 week. So, and it turned out the drug combination I picked on was 2/3 of what they use for peptic ulcers. So I went to the pharmacist. He said, "You're missing the other one." I said, "What other one?" So it's the one for peptic ulcers. Combinatorial approaches sometimes are marvelous. So it's good to talk to your doctors and explore some options, because I was having a very persistent disease, and it turned out a combination of oral antibiotics was all I needed. But the doctors didn't know that. So it's a good point with some of that.
Well, I went through this in 2009, and MRSA moves so fast you wouldn't believe it. It's so potent. But they caught this with experimentation, and they got it like on my fourth or fifth day in the hospital, and it saved my life. Ironically, in 2021, one of my best friends from high school died from this. And if he'd been one of those people that like to communicate over the phone or email, I'm pretty sure I could have saved his life, because he died from a pretty virulent MRSA infection.
Yeah. I have one of those where if I'd said one sentence to a friend, I might have prevented his later death. And it's tough, because I will never, that will always come back and haunt me, because I came so close to giving him a little warning about what might happen due to some of the press coverage he was getting. And I didn't. And he wound up committing suicide. If I just told him, watch out, he would have realized what was going on. And instead, he just took it very personally and unfortunately made the bad choice. So yeah.
Terry, speaking of technology and suicide and the internet, there was a young man who I think is given credit for inventing Reddit and stuff. His name was Aaron Swartz, and he went to a technology conference in Italy, and one of the session leaders talked about the evilness of JSTOR and MIT. So, young, brilliant Aaron Swartz decided to write some routines that downloaded about 550,000 documents out of JSTOR, and MIT reported him. The FBI came in. He got charged under the Computer Fraud and Abuse Act of 1986. He realized he was looking at $1 million of legal fees to stay out of jail. So he killed himself. And if I could have a conversation with that young man, I'm very familiar with Phil Zimmerman. I know Phil Zimmerman, Mr. PGP, and I knew personally about Randall Schwartz in Intel. I could have helped Aaron Schwartz crowdsource his legal funding, and the internet would have handsomely contributed and saved his life. But
Yeah.
he was desperate, so he killed himself in January of 2013.
That was a very sad story. I remember that one. That was sad.
Yep.
And like you say, there are so many other opportunities people don't realize with that. But the idea of JSTOR being evil, that's strange.
Yep.
I'm not in a world where that statement even makes sense. But wow. Okay. Any other questions?
Yeah, Terry will be back on September 13th and I think October 12th.
I've got one each month until the end of the year, and
Yes.
one of them is pursuing that $1 million prize, different strategies which is that's kind of bogus because the way they set up the rules, even if you won the Millennium Prize for that particular problem, it would take you 10 years to get it because it would have to be published. There's a whole set of rigmarole you have to go through. But in terms of solving the problem, it's an interesting problem. So I think one of my talks about that. I don't remember that's the next one. I'll have to look at the schedule. And I do have a talk about special relativity coming up. So that should be interesting.
Hey, Terry, real quick. I did post the stuff about our Chicago Quantum Hackathon. So if a little bit later in LinkedIn chat or email, I can brainstorm with you about raising the money for the prizes. That would be really helpful because I can't fund this myself, but quantum has gotten so hot right now. I think some people would be happy to write some checks if they could see the positive outcomes of this 30-day hackathon.
Okay. Let's get in touch later and we can talk it over.
Sounds great.
Yeah, Maya says she can't wait for those talks from Terry, probably. Yeah. Yeah, if you have more talks, let me know for the 2026. Yeah.
Okay. Will be. One of the things I might do, Helen, is just go into a micro dive on some of the more radicals. I've had ones where people have made the comment that, I could do a whole presentation in one slide. Some cases I might try doing that if that works out okay with you, because there's some where I'm hitting a topic that's very different from standard, but I have a lot of reasons for going with that. One example is space empty or is space full of quantum foam? That's a worthy topic to address in detail because the quantum foam idea has been developed and looked at carefully, and there's all sorts of reasons why it's partially right. See, that's the trick. Partially right is not the same thing as fully right. And sometimes you have to look at the foundation. So I might do topics like maybe some smaller ones next year.
Sure. Thank you.
Okay, thank you.
And today, thank you for your wonderful talk.
Okay, thank you.
Yes, we're looking for your next one on September 13th.
Okay, looking forward to it.
Thank you, Helen and Terry.
Helen, you are the best.
Thank you.
Thank you.